Hello everyone, welcome back to another discussion in dynamics. Today we will talk about impacts. Namely, we will talk about direct impact, oblique impact, and coefficient of restitution. And I just want to remind you that we are still in the momentum chapter. Plan for today is a brief lecture review and then two examples. Without further ado, let's dive straight into our discussion. Let us start today with a brief lecture review. So I just want to let you know what direct impact is. So please imagine that we have such a situation. We have two bodies, two particles, that they are about to hit each other. So you can see that based on their geometry, we can specify line of impact. This is line of impact. It goes through the center of masses of these particles. And in direct impacts, we have velocities aligned with the line of impact. Okay, so this is the characteristic thing of the direct impacts. Velocities are aligned with line of impact. In oblique impact, situation looks a little bit different, because if we consider a very similar situation, so we have again two bodies that are about to collide. So again, we will have here our line of impact, but just to save some ink, I'm just going to write an abbreviation, LOI. So in this case, our velocities do not have to be aligned with line of impact. So let's say that this is the pre-impact velocity. Of body A. And this will be pre-impact velocity of body B. Okay, so that's the difference between these two cases. And now I would like to focus on coefficient of restitution. And I would like you to imagine such situation. I would like you to imagine situation pre-impact and post-impact. And in here we will have, again, two bodies that are about to collide. And they will have some velocity, right? Velocity A and velocity B. Maybe I will even do it like that. So pre-impact velocity A must be larger than velocity B, at least in this case, yes? Otherwise, otherwise body A will never chase body B, right? And post-impact situation will look like that. Like that. That will have velocity A again, but this time that velocity will be a little bit smaller than velocity B. And I believe that in the lecture, in this course, the notation is following, that pre-impact we put pluses here, yes, in the superscripts. No, minuses here, minus here, minus here, and plus here, and plus here. Just to distinguish these velocity components, pre-impact and post-impact, right? This is the notation you've seen yesterday in the lecture. However, I don't like it. I don't like this notation because I kept forgetting what these pluses stand for and what these minuses stand for, okay? I would like to introduce my notation, okay? So let's please forget, at least during this discussion, please forget about these pluses and minuses. And instead of them, I would like to put here superscript pre. And in here, I would like to put superscript post. Okay? In such with such notation, I will never be confused which velocity stands for what. Okay, now we know what happens pre-impact and post-impact. Of course, if you prefer the notation with pluses and minuses, it's a free word. Go for it. I prefer this one. I'm gonna use this one. Okay, and now the definition of coefficient of restitution. So I believe that E is equal to difference in velocities post-impact divided by difference in velocities pre-impact. And let's write it explicitly. So I believe that post-impact, we already said that velocity B must be larger than velocity A, right? So in here we will have velocity B post minus velocity A post. In pre-impact, we must assume that velocity A is larger than velocity B. So in here, velocity A will be first. Velocity A pre minus velocity B pre. Okay, and this is the definition of our coefficient of restitution. This and that. Any questions so far? No questions. This is just a review, right? Yeah. But I would like to say one more thing, because this definition that you see right now on the board, it corresponds to the situation in the drawing. And what do I mean by that? By that, I mean that every single velocity points towards the right. Okay, so this expression is true if you assume in your solution that each of these four vectors point towards the right. This is true if this, and that points that way. Okay? Let me mess around with that picture, okay? So look what will happen to that equation if, for example, we have such situation. If our VB pre-impact points towards the left. It can also be true. Yeah, it will also be an impact. So then I must modify my definition. I must flip the sign in front of VB pre. So basically in here we have a minus. So instead of that minus, I will put plus in here. Okay, so now you can see that this equation corresponds to the situation in the board. And the reason for that is that momentum is a vector quantity, okay? So we must take care of the directions of these vectors. Maybe, for example, after the impact, you would like to assume that VA post points this way. If you would like to assume this scenario, then you must flip the sign in front of VA post. So you should put plus in here. Okay, so now you can see the situation in the picture corresponds to this definition of the coefficient of restitution. Am I making you confused, or is it clear? Yes? Okay, cool. So I prefer when all of them point towards the left, okay? So I'm just going to leave this situation on the board, okay? So today we are just going to assume that everything points towards the left, towards the right, towards the right. And we are just going to go for this definition. Okay, guys, I'm done with the review. Do you want to do examples? Okay, example number 1. Here is the problem statement of example number 1. So please read and understand the problem statement before we start our resolution. I also have an attendance list in here. So for those of you who were late, please approach me after the discussion and put your name on the list. People walking there, looking at us, I don't know. What do you want to ask? Okay, so what do we have in here? We have two bodies, right? We have bag A and body B here. And we will again model them as particles. And I think that particle A has to travel a little bit, right, along this trajectory before it hits our body B. Okay, so we will have a hit in here, yeah? So that bag will be here, and it will have some velocity. It will have some velocity. Velocity A. Yeah, and what else do we know? We know their masses, and we know that the coefficient of restitution between these two bodies is 0.5. And they ask us to find velocities right after the impact in part 1 and the energy dissipated during the impact. We will focus on that in part 2. However, before doing part 1 and part 2, I think that there is a implicit part 0, right? Because we must figure out what is this velocity, that velocity A pre-impact. Yeah. So there is like a silent part 0 where we have to use work energy method in order to figure that out. Yeah. Work energy method. So I will just write down this equation. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. Obviously, subscript 1 corresponds to this configuration. And this will also be my datum. And subscript 2 in this equation corresponds to this configuration. This is subscript 2. Okay, and we must find these 5 guys. T1, V1, T2, V2, U12 non-conservative. Okay, I believe that our body starts from rest. And at configuration 2, we have some velocity. So in here we will have 1/2 ma VA squared. When it comes to potential energies, our body is aligned with the datum at configuration 1. And at configuration 2, our body is below the datum. So in here we will have minus MAGL. And I think that every single force, every single non-conservative force that is present in the system does 0 job. Okay, let's plug in these 5 guys in our equation. So we will have 0 that is equal to 1/2 ma VA squared minus MAGL. And you can see that our VA is basically square root of 2GL. And if you plug in values and grab your calculators, you will obtain that our VA is approximately 13.9 feet per second. And this will be our VA pre-impact, of course. Okay, I'm done with part 0. Any questions? Cool. So now we will focus on the impacts, okay? So we will have part 1. Which is direct impact. So I'm just going to start with a drawing, as I usually do. So in here, I just want to show you the situation pre-impact and post-impact. So I believe that pre-impact, we have our bag in here, and it has some velocity. It has some velocity VA, or actually some momentum MAVA. And our block is motionless, right? Our VB pre is 0. And post-impact, we have following situation. I want to assume that all of them point towards the right, okay? So I just want to assume that in here we have VB post and VA post. Okay. And these are our unknowns. I will mark unknowns with red. We don't know this value. And we don't know this value. Okay, so I just want to remind you that during the impacts, momentum is preserved. So we can write it down. Linear momentum preserved during the impacts. Linear momentum preserved during impacts. So I can write down linear momentum equation. Linear momentum equation. And let's assume that this direction is positive. So at the beginning, we will have MA VA pre that is equal to MA VA post plus MB VB post. Okay, and we have one equation and two unknowns. So we need second equation, right? And this is where coefficient of restitution comes into play. We will just go for the coefficient of restitution equation just to find the second equation. So now coefficient of restitution. And I think that by definition, E is equal to delta V post divided by delta V pre. And that means that VB post minus VA post is here. And in here we will have VA pre minus VB pre. Okay, and I think that pre-impact body B was motionless, and velocity of body A we found in part 0. This is 13.9. I think we found second equation, because in here we can see that our VB post minus VA post is equal to 13.9 E. Okay, guys, we have two equations and two unknowns. The rest is mathematics. So let's solve it quickly. So in here we will have MA VA post plus MB VB post, and this is equal to MA VA pre minus VA post plus VB post, and this is equal to 13.9 times E. Clearly we have two unknowns. This is not known, and this is not known. And these are two linear equations. So let's plug in values and solve it. So in here we will have 6 divided by 32.2 VA post plus 18 32.2 VB post. The VA pre was 13.9 And in the second equation, we have following situation. And this is equal to 13.9. And I think that coefficient of restitution was half. Okay, grab your calculators and find that our VA post is something and VB post is also something. I must double check what I obtained yesterday. Okay, in here I got minus 1.74 feet per second. And in here I got 5.21 feet per second. Okay, so it looks like my assumption was incorrect. However, before talking about that, I see that there is one question, Olivia. They would be stuck together if this guy is 0. So as you can see, this is a little bit of review, Olivia, especially for you. So if our coefficient of restitution is 1, that means that our collision is perfectly elastic. Okay? Perfectly elastic. If our coefficient of restitution is 0, that means that it's perfectly plastic. And only in that case, our bodies will be glued together afterwards. Okay, only in that case. However, in that case, we must solve the problem in the way I presented for you today. Is this answering your question? Yeah. So they are not glued together. This is my answer. And that was your question as well. Yes. You asked me why they are not glued together. Yes. Yeah, I was wondering why. Don't worry. I kept forgetting many different things. Don't worry about it. Do we have any other questions? I don't see any. So I just want to show you one more thing, because it looks like my assumption was incorrect. Yeah, because we obtained a negative value here. We obtained negative value here. So that means that post-impact, our velocities will look like that. Our VB post will be 5.21 pointing this way, but VA post will be pointing this way. Our bag will rebounce off of that block. So this VA post will be pointing this way, and it will have magnitude 1.74. Okay, so this is the answer to part A. But we also have part B, I believe. So let's now scroll up the board and remind ourselves what they ask us for. Aha, they ask us to find energy lost during the collision. So I think that again we should go for the energy equation, right? So in here we will go for part 2, and we'll go for T1 plus V1 plus U12 non-conservative, and this is equal to T2 plus V2. I believe that our potential energies do not change during the impact, so we can get rid of that. And we can simplify our equation to a following form. So the energy lost during the impact is basically a difference between kinetic energies in this case. And our goal is to find u-12 non-conservative. So we have to find what is T1 and what is T2, where of course T1 corresponds to the situation pre-impact and T2 corresponds to the situation post-impact. Okay, pre-impact we had only one body moving, body A, and it had 1/2 ma va pre-impact squared. Let's plug in values. So in here we will have 1/2 6 divided by 32.2, 13.9 squared. And if you grab your calculators, you will obtain that this is equal to approximately 18.0 pound-feet. Yeah, I solved it yesterday and I obtained here, I believe, 18.0003 or something. Yeah, so 18.0 is fine. When it comes to situation post-impact, you can see it in the top right corner of the board. And in here we have two bodies that have velocity. So in here we have 1/2 ma va post squared plus 1/2 mb vb post square. And if you plug in values and grab your calculators, you will obtain that this is approximately 7.869 pound-feet. Okay, so that means that our u-12 non-conservative is equal to approximately minus 10.132 pound-feet. And this is our answer. As you can see, we obtained negative value for energy. That means that our energy is dissipated during the impact. Yes, we are going to lose some energy. Okay, any questions? Okay, I don't see any. So what now? Would you like to do example number 2? Okay, let's do it. As usually, please take a couple of seconds and read and understand the problem statement. So what do we have in here? We have one particle this time, this particle, and that particle is moving on a horizontal surface. So in the picture, you can see actually a top view of that situation. And that particle will hit this wall that is fixed. And pre-impact, our particle has velocity v0. The incline of that wall, or the angle of that wall, is 45 degrees. And the coefficient of restitution between the wall and the particle is, again, 0.5. They ask us to find velocity after the impact. So let's do it. So I'm going to start with a drawing. I'm just going to show what happens before the impact and after the impact. So in here we have that wall. This angle is 45 degrees. And that wall is fixed. And our particle is about to hit the wall. And in here we have our line of impact here. It will be perpendicular to the surface. This is our line of impact. Okay, so let me copy this drawing here. And I believe that before the hit, our particle has such velocity. This is our v pre-impact. right? And I believe that this one is equal to V0. Maybe I can put it here. V0. Okay, so this is not a direct impact, yes? This is oblique impact, because clearly our velocity is not aligned with the line of impact. In such problems, your first step is to project that velocity onto line of impact and the direction that is perpendicular to the line of impact. So we must find these two projections. This one and this one. So this guy will be V pre, but in the normal direction. And this guy will be V pre, but in the tangential direction. And since our angle is 45 degrees, I think that they are going to be equal to each other, right? I think that this guy will be basically square root of 2 divided by 2 V0, and this guy as well will be square root of 2 divided by 2 V0. Okay, and our goal is to find what happens after the impact. So let me assume these two velocity components. We will have V post tangential direction, and we will also have V post normal direction. And we do not know them right now. We do not know what their value is. We don't know this one and we don't know this one. So how to solve such problems? I usually start with tangential direction because it's super fast. In such cases, nothing changes in tangential direction, nothing. So basically I can copy paste what we have on the left hand side and paste it on the right hand side. Basically what I'm saying is that VT post is equal to VT pre impact. And this is equal to square root of 2 divided by 2 V0. That's all. 50% of the problem done. But something changes along the n direction. And in order to figure out what this value is, we just must repeat the strategy for the direct impact. So now let's focus on the n direction. So in here, I'm just going to go for this definition of coefficient of restitution. E is equal to V post n divided by V pre n. This formula is a simplified formula we already seen in this discussion. I just simplified it because this is just an impact against the wall that is fixed. So our wall is motionless regardless of anything. Plus also, when it comes to impact against the wall, I usually assume that our particle approaches the wall before the impact, and it increases the distance after the impact. Yeah, so basically the velocity points towards the wall before the impact, and it points in the opposite direction after the impact. Okay, and I think that the problem is done. Yes, because in here we have only one unknown. This is the only unknown we have in here. Oops. So our V and post is just E times V and pre. Let's plug in values. 0.5 times square root of 2 over 2 V0. And this is basically, that means that our V and post is square root of 2 over 4 V0. That's it. So I can get rid of this question mark. Square root of 2 over 4 v0. Okay. So let's also draw the situation post-impact. So I can take that drawing. I can put it here. And I believe that I must shrink one vector. Yeah, I think that this guy will be twice shorter. Yeah. And this is our velocity post-impact. Oops. Here and here. V post. This is our vector post-impact, and you can see its components on the board. That's all I prepared for today. Yeah, I have one more thing to say to you guys, but it will be off camera, okay? So, in case are there any questions? I don't see any. So, thank you for today, and see you next time. Bye bye.